In this video, we're going to be looking at what happens when we build a model where we also allow for categorical predictors. And in particular, in this class, we're only going to focus on the very simple case where it's a binary predictor, meaning that there is only two categories possible. Because we can still use that information in a regression model to try to predict the response variable with that additional information. We won't do a whole lot of exploration of this topic, but we'll do kind of a very basic situation that might be helpful. So yeah, a binary variable is going to be a variable, a categorical variable that has only two categories. Sometimes you hear them called two levels if you take more courses. But yeah, so we can also do this with three or more categories as well. We're not going to do that in this class because it's a little bit more complicated. So we're just going to focus on what happens if we have two categories. So what's going to happen here is we're going to assign one of these categories, one of these levels to be 1 and the other to be 0. And then whether or not the one category is true determines if we make an adjustment to our prediction. And if the 0 category is true, then there is no adjustment to be made, and the model as it stands is going to represent that 0 level. So we use the term dummy variable in this case because in a way we're kind of extracting our information to the simplest possible form. So instead of retaining kind of these category names, we're only just using the 1 and 0 notation to just kind of say like either this category is present or this category is absent. And so when we had this kind of trivial case of two categories for just one variable, it doesn't matter that much. But if we did a model where we had a categorical variable with three or more categories, then we have to actually create a new dummy variable for each additional category as well. So in other words, we have a base level, and then we have a second category that has a dummy variable, a third category has its other dummy variable, a fourth category, etc. And those would each be individual terms that either are added or not, depending on which one is true, which one is the one showing up. So we're not worrying about that case because that's a little bit more complicated. We're only worrying about this binary variable where there's two categories. So either the one category is true and we add a term to this model to adjust our prediction, where the other category is true and we don't add that term and our model stands to represent that other category. Okay, so let's take a look at an example to kind of enlighten this, because it probably feels a little bit abstract with me just describing what's going on with an equation here. So let's say that we're trying to predict recovery time for patients after a car accident. And we're going to use some information from the accident to try to predict how long we would expect them to be in the hospital. And this is very simplistic, the way we're doing this. I mean, if we were doing this in real life, this is probably not the most helpful model ever. We'd probably have a lot more variables we'd like to consider. But we're going to do this with just three predictors, just to make this as simple as we can. The first is going to be the patient's age. The second is going to be the impact force of the accident they were in. And the third is whether the patient was wearing a seatbelt or not at the time of the accident. And so if the patient was not wearing a seatbelt, we're going to label that as 1. And if they were wearing a seatbelt, we're going to label that as 0. So in other words, if they weren't wearing a seatbelt, then we are going to adjust our prediction. Whereas if they are wearing a seatbelt, our model is going to stand as it is without that adjustment. Okay, so to make this model, to try to kind of understand how these variables relate, we have information from 77 non-fatal car accident victims between ages 18 and 73. And they all needed to stay at least one night in the hospital. And we're going to use this information to try to predict their recovery time in the hospital based on this predictor information. So again, this is a model. It doesn't mean that this model tells us exactly how long somebody stays in the hospital. There's still going to be some error. There's still going to be some unexplained variability in that response variable. But this gives us a prediction, and it gives us a little bit more accuracy than we would have if we didn't have this information, right? So there's a lot of variability in this hospital stay variable to begin with. And knowing this information helps us predict a little bit more accurately where that is going to end up. All right, so first let's use our intuition, and maybe this is a good place for you to pause and think about it. Which predictors do you think will be positively correlated with recovery time, and which do you think will be negatively correlated? And I guess I'll move myself out of the way. So of these three predictors, which ones, or how do you think this correlation with recovery time is going to wind up? So I'll tell you my intuition here. I would think that with age, the correlation is probably going to go up, meaning that the older the patient is, the longer I would expect the recovery time to be. But I do need to mention something here, because you might also be thinking about this as possibly negatively correlated, where you might be thinking, well, maybe younger people are more likely to be in serious accidents than older people. And I think that's a really fair statement. And if we were doing a simple model with age as the only predictor, I think that's a real possibility. However, since we're doing multiple regression, notice that we do have other variables here, including impact force and seatbelt wearing. So the coefficient that we're going to see for age in this model is for comparing two patients who were involved in accidents with the same impact force, who had the same seatbelt status. So given that these two other variables are holding constant, the coefficient for age, I would expect, is going to be positive, meaning that for two patients where these two things were the same, I would guess that patients who are older will probably have a longer recovery time. It's possible I could be wrong. It's possible there's other confounders here that also keep that relationship backwards until we add them in. But given these other two predictors in the model, I think that age is probably going to lead to longer recovery time if holding impact force and seatbelt status constant. And again, this is just my intuition. I think it's just good to kind of think about it this way before we look at the model, because sometimes we look at the model and we see the values and we stop thinking contextually what we're doing. So this step, I think, is kind of helpful first to remind ourselves what we're doing, I would guess. And then along that same line, I would think, again, impact force would probably be positively correlated. Certainly if we're controlling for age here, so two patients of the same age but of different impact forces, I would guess impact force would be positively correlated with how long recovery time will be. Seatbelt status, we can use this term correlated, but since this is a binary variable, it's kind of hard to think of it with that word because we can't say positively correlated exactly. But really what we're just saying is that there's two categories here, and which one do we think is associated with longer recovery time? I would think it would be the no seatbelt group. So I would think if you're not wearing a seatbelt, you are more likely to have a longer recovery time. Or I guess, no, I should say longer recovery on average. So this is my intuition about how these variables will probably fit into the model. Maybe you thought about it a little bit differently, but again, this is just kind of our entry point into the context so that we're thinking carefully once we see our model and what these values mean. So let's see if these intuitions are correct, and it looks like they are. So age is positively correlated when controlling for impact force and seatbelt status. Impact force positively correlated when controlling for these other two things. Seatbelt status, so when not wearing a seatbelt, there's a positive value, meaning that recovery time is longer on average for the non-seatbelt wearers. So that intuition that I shared earlier seems to be correct with this particular model. Okay, so let's go ahead and interpret these coefficients, again, consistent with multiple regression, where we are talking about the average relationship between this and the change in the response variable when the other predictors are staying the same. So when comparing two people where seatbelt status and impact force are the same, what do we see as the effect on recovery time when age is changing? So for every 1 unit increase in age, we expect recovery time to increase by 0.21508. as the other predictors are holding constant. We can do the same thing with impact force. So for every 1 unit increase in impact force, we expect recovery time to increase by, and this is a really small number, by the way, 0.000812, because that is 8.12 times 10 to the negative 5. So that means that we have to move the decimal place 5 places, which is what we did there, as the other predictors are holding constant. One observation I always like to point out at this point, you might be looking at these coefficients and thinking, wow, so it looks like impact force has a lot smaller effect on recovery time than age. And if you're talking about by unit increase, the answer is yes. However, you have to remember that these variables are represented in different units. So for example, a 1 year increase in age is very different than a 1 Newton increase in impact force, because impact force in newtons is going to be a really huge measurement unit. And when I say a huge measure, I guess actually it'd be the opposite. It'd be a really tiny measurement unit. So impact force in car accidents are probably measured in the thousands, but more often in the tens of thousands or maybe even above 100,000. So yes, a 1 Newton increase in impact force probably doesn't matter that much. However, impact force is actually a highly statistically significant variable here, meaning that we're super, super, super confident this is having an effect here, and it's probably having a pretty large effect when you think about how 1 Newton is a really, really tiny change, and that if you have one car accident and then you have another car accident that to our eye might seem just a little bit stronger, it's actually probably going to be, a couple thousand newtons stronger than the other one that we just witnessed, even though it might seem like it's a very small difference. So I point this out, and that you can't really use the coefficient to judge how meaningful the predictor is and how strong the relationship is, how much it's contributing to the model. So even though the coefficient is just in the unit of the variable that we're looking at, but this in itself can't really tell us how strong the relationship is. So just kind of keep that in mind. Or maybe, something else I'll mention up here. It's when I say the units, I mean, think about it this way. If I'm comparing, let's say that I'm trying to look at how foot length might be correlated with your height. But the coefficient that I record for a height is going to depend on the unit of height measurement that I'm talking about. Because if I was talking about measuring height in feet, that's different than meters or inches or centimeters, right? And so the coefficient is going to change depending on what that unit is. If I'm using a really tiny measurement like centimeters, then this is going to be a really tiny coefficient. If I'm using a really big unit like feet or meters, then this is going to be a really large coefficient. So I hope that example just kind of helps that the value of the coefficient itself doesn't tell us how strong the predictor is and how much it's contributing to the model. It's only a representation of how 1 unit of that particular unit corresponds to a change in the response variable. Okay, so we interpreted impact force and age, but how do we interpret the seatbelt coefficient if this is a binary predictor? We can't say for every 1 unit increase in seatbelt use, right? That doesn't make any sense. And so what's going to go on here is that this coefficient is representing the average change in recovery time when somebody doesn't wear their seatbelt in comparison to someone who is. So if I have 2 people of the same age and same impact force, one of them is wearing a seatbelt and one's not wearing a seatbelt, this is my best guess for their difference in recovery time based on that information. Again, there's still a lot of variability here, right? So maybe that recovery time for 2 particular individuals with the same age, same impact force is a lot lower. Maybe it's even negative. Maybe it's the other way around for 2 particular individuals. And maybe there's 2 individuals where that recovery time difference is really high, like 5 or 10 days. So that can still happen. But this is my kind of estimate for that average difference between any 2 people who had the same age and impact force, according to what I found when I looked at these correlations all together. All right. So with that said, I'm going to interpret the level, the category where someone's not wearing a seatbelt. So that's the one that's showing here. So notice that the no is showing up, meaning that that is the category represented with this coefficient, is not wearing a seatbelt. So if the participant's not wearing a seatbelt, then we would expect recovery time to increase by, that would be 3.05672 on average, as the other predictors are holding constant. Again, I really should be saying on average here to be super consistent, by this amount on average, because again, with individuals, it might be a little bit different from individual to individual, but this on average is what I'm observing, as the other predictors hold constant. So I can put that all together into an equation. And if I want to make particular predictions for recovery time for an individual based on their information for these predictor variables, I can do that. So can I predict the recovery time for someone who's age 41, was in a car accident with impact force at 45,000 newtons, and was wearing a seatbelt? So I'm going to do y hat equals negative 0.9566 plus 2.21508 times their age is 41, plus their impact force is 45,000. And they were wearing a seatbelt, which means that this is going to be the 0 category, right? Because not wearing a seatbelt is 1, as this model defined it. Wearing a seatbelt is going to be 0, which means that this term is just going to go away. We're not going to add it in. So the remaining equation then represents people who were wearing a seatbelt. This would be the adjustment I make for somebody who wasn't wearing a seatbelt. Okay, so then I'm going to sort of add this in. So I'm going to do negative, oops, is that right? Yeah, 0.9566 plus 0.21508 times 41 plus 0.000812 times 45,000. And I get about 11.51 or 11.52, I guess, if I round this. So this would be my best guess for recovery time for someone with this accident information. It doesn't mean that they will have this amount of recovery time. There's still variability, there's still error in my model, but this is my best guess. That's hopefully more accurate than if I just used y bar without knowing any information, because there's going to be a lot of variability in recovery time. So this is hopefully helping me make a slightly more accurate prediction than I would otherwise.